So, hello students, good afternoon. Good afternoon or good evening to all of you. So, just let me know, am I visible and audible to all of you? Yes, good afternoon. Am I visible and audible? And can you see my screen? Yes, thank you, Himavashini. Good. Yeah. So, today we are going with a new topic called coordination compounds. And by the way, my name is Anandi and I'll be dealing with the coordination compounds for you. Okay. So now, coming to the lesson. What are coordination compounds? What are coordination compounds? So they are the specific type of compounds formed by certain elements. They are the specific type of compounds formed by certain elements. And what are those elements? Those elements can be a metal and a atom. It can be an anionic system or neutral atom. Okay. So the other atom can be neutral atom or it can be an anion. So this anion or the neutral atom comes with its electron and forms the bond with metal. So now this metal and this particular atom, so both together are called as coordination compounds. So who are these two dots? These two dots represent the two electrons coming from the neutral atom or the anion. Okay. So which is donating the electrons to the metal actually. Now it is a complex or coordination compound. And let us see some coordination compounds in biological systems. So you all would be aware of this, no? Chlorophyll. It is a coordination compound which has magnesium metal at the center, which is present in plants. And in hemoglobin, you can see the Fe atom, iron atom at the center of the complex, which forms the iron metal complex. And in vitamin B12, it is a cobalt metal complex. So the magnesium is an S block metal and iron and cobalt basically are P block metals. And in most of the coordination compounds, you can find the D block elements. Yes, D block will also be there, like magnesium, aluminum will also be there. But most of the metal atom will be of iron and cobalt. Okay. So these are also the coordination compounds in biological system. And one more. So cisplatin. So cisplatin consists of platinum metal, which is again a D block metal. It is used as an anti-cancer drug, no? So cisplatin is the one which is used for the treatment of cancer, which is a coordination compound basically, which consists of chlorine ligands and NH3 ligands. I'll discuss what are ligands in the next slides, okay? And what are the applications? So some of the applications of coordination compounds are, you can remove the hardness of water by calcium ethylene diamide tetraacetate complexes. So the hardness of water can be removed by a corresponding particular coordination compound, which is called as calcium EDTA complex, so that the water becomes soft. So what is the difference between hard water and soft water? So hard water contains some calcium, magnesium, bicarbonate ions, etc., etc. So we have to remove all those ions. Then only we can use it for drinking purpose. Only soft water can be used for drinking purpose. Okay. So the hardness of water can be removed by a coordination compound. So these are the applications. And extraction of metals. So to get the pure metals like silver and gold, in the purification process, before the purification process, some more steps will be there. In that steps, the coordination complex is formed. Okay, from that coordination complex only the pure silver, pure gold will be extracted. So all those we will discuss in the next slides. So these are some of the applications. And now coming to the introduction to coordination compounds. So today we are going to discuss about the Werner's theory and some of the basic terminologies pertaining to coordination compounds. And as I told you, the ligands and the nomenclature of coordination compounds. Okay, we'll go as time permits with the 4 topics. Now coming to the Werner's theory, which is the first topic for today's class. So this Werner, so his full name is Alfred Werner. So what he did an experiment in his lab. Okay, he did an experiment in his lab first. He is called to be the father of coordination compounds also, because he was the one who discovered the first coordination compound. So what he did in his lab was, he took cobalt chloride and ammonium containing salt. Cobalt chloride salt he took with 6 ammonia molecules, he took in one test tube, and he added the AgNO3 to that cobalt chloride 1 mole compound. Okay, and he got 3 moles of AgCl precipitating out. He got 3 moles of AgCl coming out from the reaction. So what is the meaning of that? Only 3 chlorine molecules has combined with the AgNO3. Only the 3 atoms, 3 chlorine atoms from the salt has reacted with the AgNO3. That is the meaning he got. And secondly, what he did, he took 1 mole of cobalt chloride 5NH3 molecule and he added the same AgNO3. But here in the second case, he got only 2 moles of AgCl. So what is the meaning now? Only 2 out of 3 Cl atoms has combined with AgNO3. Okay. And the third observation was, he took 4 ammonia molecule containing cobalt chloride salt and he added the same silver nitrate to that. And now he got only 1 mole of AgCl precipitated out. What is a precipitate? Something which is settled at the bottom of the test tube while doing the reaction. Okay, that is called as precipitation. AgCl is precipitating. Now, from this third observation, he concluded that only 1 chlorine out of 3 is reacting with AgNO3. Now, again, for the same complex, he added AgNO3. Same observation was observed, and now these two complexes are having different colors. One is green and the other one is purple, right? So if there are 2 different compounds, if there are 2 different colors, it means that both are different. Even though the formulas are same, they are different compounds. Okay, let's discuss about those different compounds in the upcoming slides. Okay, so this was the experiment done by Burness in his laboratory. So from this experiment, he concluded something. And before that conclusion, he also did conductivity experiments in his lab. He did some conductivity experiments. So for the first salt, which is having COCl3 and 6NH3 formula, he got 1:3 solution of conductivity. Means 1:3 electrolyte in the sense only 1 cation and 3 anions are there in the system. And for the second compound, he got 1:2 electrolyte, means only 1 cation and 2 anion. For the third compound, 1:1 electrolyte, and for the fourth compound also 1:1 electrolyte. Okay, so these are the results he got from the conductivity experiments he did in the lab. Okay, now from these 2 experiments, he concluded some things. So what are those things? So for the first compound, he got 3 moles of AgCl, no, and also 1:3 electrolyte he got, right? So what he is trying to conclude from this particular first observation is, there is a formation of CONH3 6 times 3 plus and 3 Cl minus ion. So here you can see there is only 1 cation and there is 1 cation and there are 3 anions. 3 anions. So that's why the solution is given 1:3 electrolyte. Okay. And also there are 3 moles of AgCl precipitated out, right? So it is because of the 3 moles of AgCl. 3 Cl minus, as you can see. So that's why he got 3 moles of AgCl. And from the second experiment, he got these results. For the second compound, he got these 2 results. Now he is concluding the formation of compound would be of this type. There is 1 cation and 2 anion, since 2 AgCl are precipitating out. Okay, and for the third observation, this is your complex, which consists of 1 cation and only 1 anion, which is Cl minus. And for the fourth compound also, the same thing. Okay, formula is same, but the structures are different. I'll let you know that. So these are the conclusions he made from the experiments he did in his lab. Now, he started studying these compounds. He represented these compounds in square bracket. No, he started studying these compounds and named those compounds as coordination compounds. Okay. And from his experiments and conclusions, he is giving his postulates, and those postulates we are calling it as postulates of Werner's theory, which is very important. And he is saying that coordination compounds consist of two different types of valency. One is primary valency and the other one is secondary valency. So what are primary valency? Primary valencies are ionizable, whereas secondary valencies are non-ionizable. And primary valencies are satisfied by negative ions, and here the secondary valencies are satisfied by negative ions or neutral atoms. Okay. And primary valency is nothing but the oxidation state, and secondary valency is nothing but the coordination number, and that particular coordination number is fixed for a particular system. Okay. So all the ligands, all the components which is attached to the central metal atom, they will have different spatial arrangement, so that it gives different structures, and they are related with the different spatial arrangements for different coordination number. If the coordination number is 4, then the arrangement would be different. If the coordination number is 6, then the arrangement of the atoms will be different. So like that, they have different spatial arrangements. Suppose if I am taking this particular compound, the coordination number is 6. The coordination number is 6 because, so cobalt is the central metal atom. So to this central metal atom, 1 chlorine is attached and 5 NH3 ligands are attached. So what is the coordination number? 6. 5 plus 1 is 6. So which is nothing but the secondary valency. Now, what is the primary valency? It is 2. Why the primary valency is 2? They are ionizable, right? So the 2Cl minus can be ionizable. They are coming out. So the primary valency is 2. Or you can find the oxidation number from the given complex also. So I will tell you how to find out the oxidation number and all for the coordination complexes in the next upcoming slides. Okay. So what are primary valency? Primary valencies are oxidation state, and the secondary valency is coordination number. Very simple. So this was the first postulate given by Werner. Okay. They are ionizable. Primary valencies are ionizable and secondary valencies are non-ionizable. So all these points you have to keep it in your mind. So shall I move on to the next postulate? Any doubt so far? So if you have any doubt, put it in the chat box. Okay, I'll explain you again. Now, the different spatial arrangements which I have told you for those last two complexes, they are these, and the first, the color of the first complex was green and the second was violet. So why we are observing two different colors? Because of the different spatial arrangement of the molecules or the ions around the central metal atom. So the compounds which have same molecular formula but different structures, they are called as isomers. Compounds having same molecular formula but different structures are called as isomers. Since these two compounds are isomers of each other, they are in different colors. Okay, so one is cis isomer, the other one is trans isomer. So we will discuss about the isomerism in coordination compounds later in this part. One will be cis here and the other one will be trans. These are the isomers. Now, you can see the coordination entity. So what is coordination entity? The components which are inside the square bracket, they are called as coordination entity, and the ion which is present outside the bracket, it can be in the left side or right side. So those ions are called as counter ion. Okay. Now, as I have told you, the spatial arrangements can be of many types. Okay. If the geometrical shape of the coordination compound is tetrahedral, then you will have 4 ligands attached to it, as you can see here in this example. And if the structure is octahedral, the coordination number will be 6. The coordination number will be 6. So in the first case, all 6 are NH3. The second case, 1 is chlorine and the other one is NH3. The third case, 2 chlorine and 4 NH3. So basically, the number of atoms or the group of atoms which is attached to the central metal atom is 6. The coordination number is 6, then it is called as octahedral. Okay. And there are also one more name for 4 coordination system, which is square planar. So PTCl4 2 minus is square planar in geometry. Got it? So what is tetrahedral? So NiCO. So this is tetrahedral. And octahedral metal will be at the center. So all the first 6 sites will be occupied by 6 ligands. This is octahedral. We will discuss all these geometry in detail in the later part. Just for your understanding, I am drawing now. So now this is square planar. All the 4 chlorine atoms will be there in a single plane. Okay. Suppose if your notebook is your plane, so all 4 chlorine will occupy all the 4 corners of the plane. It is square planar. Okay. Yes. So any doubt from the Werner's theory part? Do any of you have any doubt from the Werner's theory part? No doubt. So what are the postulates of Werner's theory? The main important postulate is he gave coordination compounds consist of 2 valency, primary and secondary. Primary is oxidation state and the secondary is coordination number. So in the exam in your JEE or NEET exam, they will give you a compound and they will ask you to find out the oxidation state or the coordination number in that compound. That question is very easy. Okay, you can get 4 marks so easily if you are getting question from this particular Werner's theory concept. So it is very easy. And one more point you have to keep it in mind is primary valencies are ionizable and the secondary is non-ionizable. Okay, and those things you have to concentrate more on Werner's theory. And the color of the 2 isomers you have to keep in mind that the green and violet color, 2 different colors are observed because of the isomeric property of the compounds. Got it? Fine. Now I'll go with the next topic, the difference between a double salt and a complex. So what is the first difference? Double salt can be completely dissociated into ions when it is put inside the solution or a solvent, but a complex compound do not dissociate completely into ions. Okay. So you can see a double salt on the screen. So it is KCl, MgCl2 and 6H2O complex. This is a double salt because 2 salts are there. One is potassium chloride and the other one is magnesium chloride. So it is called as a double salt. So now it is with 6H2O. It is a hydrated compound. When it is put inside the water, all the cations and anions which is there in that salt is getting dissociated. K plus, Cl minus, and here Mg2 plus and 2Cl minus. Everything is coming out. Okay. If everything is coming out, it is double salt. But in complex, you see, so this is a complex. K4FeCN6 is a complex. Okay. And when this particular complex is dissolved in water, it is getting separated into cation and anion. But the components which are present inside the coordination entity, it is not getting dissociated into Fe2 plus or ion and Cn minus ion. So such kind of ion dissociation is not observed in the complex. Okay, it remains as such. So this is a main difference. Dissociate into ions and complex do not dissociate into ions. Okay. And some of the examples of double salts are given to you. More salt, ferrous sulfate, ammonium sulfate, hexahydrate, and potash alum. KAl is support twice and 12H2O. So you have to study all the names and formulas of the double salt. And the examples for coordination complexes are also given to you, the same compounds which we have seen at the last slide. Okay, platinum complex and nickel complex. Right? Any doubt? Only one point here. Double salts can be dissociated, complex cannot be dissociated. That's all. The remaining part is to keep in mind the name of the salts and its formula. So I'll go with the second main topic of today's class, which is the basic terminologies related to coordination compounds. So what are the terms we use in this lesson? So the first term is coordination entity. As already I have told you what is coordination entity. So in a coordination compound, there will be a metal atom and there are some atoms or ions or molecules which are bonded to that metal atom. Suppose here in this case, there are four number of bonded ions or molecules present. Okay. Now, this is your metal atom. Cobalt is your metal atom. And these are the ions or molecules attached to it. Okay. Now, these together are called as coordination entity. The components which are present inside the square bracket are called as coordination entity. So, what is coordination entity? It is a metal atom surrounded by 3 chloride ions and 3 NH3 molecule. Okay, this is the first term. And coming to the second term, it is central atom. So, what is central atom? You can see 3 compounds to you on the screen. So, cobalt is the central atom in case of first compound and the oxidation state is +3. I'll tell you how to find out the oxidation state and all. And what is the name of the central atom in the second complex? Can anyone let me know the formula or the name of the central atom in the second complex? It is iron, right? Yes, it is Fe. Fe in 3+. And in, yes, Saubhagya. Good, iron. And in case of third compound, it is nickel. Ni nickel in the 2+2. So, these ions are central atom or it is also called as central metal ions. Central metal atom, central atom or central metal ion. So, 3 different names can be given to the second term. So, it is a Lewis acid. This point is very important. Central metal atoms are Lewis acid. So, why they are called as Lewis acid? Because they always accept the electron from the ions or the molecules to which it is bonded. It always gains the electron. It always accepts the electrons. Like I have showed you in the first screen, I told you, no, it always takes the electron from the molecules to which it is bonded. So, they are electron acceptors. Lewis acids are electron acceptors because they are electron deficient in nature. Lewis acids are electron deficient species. All the positively charged species are electron deficient in nature and they are Lewis acids mostly. Okay. Central metal atom is a Lewis acid. Very important point. Now coming to the third term, which is called as ligands. Okay. So in the complex, we have metal atom and the number of bonded ions and molecules. No, those are nothing but the ligands. Those are nothing but the ligands. And the fourth term is coordination sphere. Coordination sphere is more or less similar to coordination entity. Okay. So the components are inside the square bracket are called as coordination entity, right? The same is the case here. Okay. Coordination sphere is nothing but the coordination entity. Similar names only. So here you can see FeCN 6 is the coordination sphere and the one which is outside the bracket is called as counter ions. Okay. So any doubt till the 4 terms? Coordination entity, central metal atom, ligands and coordination sphere. I hope everything is clear to you. If you have any doubt, put it in the chat box. Okay. Now coming to the fifth term, which is coordination number for you. It is the number of donor sites a metal is having. If a metal is having 6 donor sites, the coordination number is 6. If the metal is having 4 donating sites, then the coordination number is 4. Okay. Number of electron pairs that can be donated to the central metal atom is called as coordination number. The number of electron pairs donated to the central metal atom is called as coordination number. Or you can define the coordination number by the number of sigma bonds formed by the ligand with the central metal atom. Number of sigma bonds formed by the ligand with the central metal atom. All are giving you the same meaning only. So there are different statements. That's all. Pi bond formed is not counted for coordination number. Actually, there will not be the formation of a pi bond in most of the complexes. There is only sigma bond. So you have to take only the sigma bond count for calculating the coordination number. Okay. Coordination number 6 will be for octahedral and 4 is for tetrahedral and square planar. So in this particular diagram, the geometry is square planar. Got it? So this is about the fifth term coordination number. Coming to the sixth term, coordination polyhedron. The spatial arrangement of ligand around the central atom. The spatial arrangement of ligand around the central atom. So how the ligands are arranged in a particular space with that metal. If it is arranged in this manner in the sense, for the first case you can see there are 6 ligands and 4 are occupied by the 4 corners of a particular plane, and one is above the plane and the other one is below the plane. Okay, so 4, you can take your notebook. Notebook has 4 corners, right? That is a square plane, and one is above the plane and the other one is below the plane. So what you have to do, you have to connect all the 4 ligands which is there on the square plane to the one which is above. You will get a pyramid kind of system, and another pyramid you will get at the bottom if you connect all the 4 to the bottom ligand. Okay, 2 different types of 2 different pyramid you will have. So it is nothing but the octahedral system. And if you're having 4 ligands arranged in this manner, like it will be like this, and 4 faces will be there. So it is called as tetrahedral. So you can find the 4 faces. So let me connect. This is the tetrahedral, and this is the front face. Okay, and this is the left face. This is the right face, and this is the bottom face. So there are 4 phases for tetrahedral, and here there are 8 phases for octahedral. 4 above and 4 below. Okay, 4 above. If you connect these 2, you will get left face, and if you connect these 2, it is right face, and this is your front face, and this is the back face. So 4 above, likewise 4 below also. So since there are 8 phases in that particular system, it is called as octahedral. And here we are having 4 phases, so it is called as tetrahedral. And if all the 4 ligands are on the plane, they are called as square planar. Okay. So different geometry arises out due to the different spatial arrangement of ligands around the central metal atom. Okay, which is nothing but the coordination polyhedron. Yeah, trigonal bipyramidal is also given, but it is very rare. Coordination complexes with this particular geometry is very rare. It is trigonal bipyramidal. So all the 3 atoms which I have connected, they are on the plane, and one is above the plane and the other one is below the plane. Okay. So you have, if you connect the 3 atoms which is there on the trigonal plane to the one which is above the plane, you will get one pyramid. And if you connect below, you will get another pyramid. So trigonal bipyramidal. Trigonal bipyramidal is the name of the coordination polyhedron. And the last one is square pyramidal. So this is a square plane, and only one ligand we are having at the top. So if you connect all the square plane ligand with the above one, you will get square pyramidal geometry. Okay. If you put one more below, then it will lead you to octahedral structure. If only one ligand is there at the top, then it is square pyramidal. Clear, students? So out of these 5, so most of the coordination complexes will fall under octahedral, tetrahedral, and square planar. Okay. So I'll go with the next slide. That is the information about the ligands. So any doubt you have so far from the terminologies which we have discussed? Central metal atom, ligands, and coordination entity, coordination polyhedron, coordination sphere. Any doubt? If you have any doubt, you can put it in the chat box. No doubt for anyone? No doubt for all. Okay. So means everything is clear to you. A person will not get any doubt if everything is clear to you, or if nothing is clear to him or she. I don't know in which category you guys will fall. I think all are falling under the first category. Am I right? I hope everything is clear to you. If you couldn't find anything, or if you feel difficult in any of the terms on the oneness theory which I have discussed, you can ask me. Okay. So I'll go with the ligands. So what are ligands? They are the bonded ions or the molecules to the central metal atom, right? So metal atoms are electron deficient, I told you, means they are Lewis acids, and the ligands are called as Lewis bases. Ligands are called as Lewis. They are Lewis. It is Lewis base. Okay. So who is a Lewis base? Lewis bases are the compounds which are electron rich in nature. So ligands are electron rich compounds and metal atoms are electron deficient compounds. Ligands are Lewis bases which give their electrons to the Lewis acids which are metal ions. Okay. So this is a Lewis acid, Lewis base, donation of electron from ligand to metal is shown to you. Now, there are some types of ligands which is being classified on different bases. So the first classification of ligands is on the basis of charge. First classification is on the basis of charge. So on this basis, it is classified into 3. One is anionic, the other one is cationic, the third classification is neutral. Anionic ligands, cationic ligands, and neutral ligands. Got it? So negatively charged ligands are anionic, positively charged are cationic. The one with 0 charge, they are neutral ligands. So let's see some examples for all the 3 types of ligands. Okay. So first, let me move on to the anionic ligand. The ligands carrying negative charge are called as anionic. So the first one is F minus, it is called as fluorido. Cl minus, chlorido. Br minus is bromido. And I minus is iodo. I minus is called as iodo. And Cn minus is called as cyano or cyanido. And O2 minus is oxo. That oxo ligand is very rare. Okay. And OH is hydroxo. SO4 2 minus is sulfate. NO2 minus is nitro or nitrito, anything you can use. And CH3CO minus is acetato. CH3CO minus is acetato. Okay. So these are the negatively charged ligands, which are called as anionic ligands. So you have to memorize all the ligand names. Okay, because you have to use all these names in the nomenclature for coordination compounds. Okay, so I'll go with the next set, which is called as neutral ligand. Acetate is common name. Yeah, in coordination complex, you have to name CH3CO minus as acetate. So here in IUPAC name, you are using acetate only. Like in case of EDTA, EDTA we are having, EDTA is a ligand, which is a hexadentate ligand. So here acetate group is there. Ethylene, diamine, tetra, acetate only we use. So there we use acetate only. Okay, fine. So don't get confused with the organic chemistry nomenclature. Okay. Yes. So the neutral ligands are again very important, which carries no charge. So the first very important neutral ligand for you is NH3. It is called as amine. So 2M you have to use. It is amine. And CO, carbonyl. You should not use carbon monoxide. It is carbonyl. And H2O is called as aqua, not water. And the NO is nitrosyl. CH3NH2 is methylamine. O2 dioxygen. CH2, NH2 twice is ethylene diamine. You have to take a note of it. Because in ethylene diamine, only 1 M should be written. In case of normal amine, you have to use 2 M. Okay. And PPH3 is triphenyl phosphine. So PH3 is phosphine. PH3 is phosphine. And all the 3 hydrogens are replaced by the phenyl groups. So it is called as triphenyl phosphine. It is a ligand. It is a bulky, big ligand. Okay. And again, NO. So the same thing falls here again. Sorry for that. So nitrosyl and the last 2 are same. Sorry for that. Just a mistake. Okay. You can just cross it out. So the very important neutral ligands are amine, carbonyl, aqua, and ethylene diamine. Okay. So these 4 ligands are very, very important. All are important. These 4 are will be using very common in most of the compounds. Okay. Neutral ligands. And coming to the last classification, which is cationic. So there is only very less cases of cationic ligand. So if you have cationic ligand, then you will have NO plus. Okay, NO plus, which is a cationic, and it is an example for cationic ligand. Okay, so NO, if it is NO, it is nitrosyl. The same NO can fall under cationic case also. So I'll tell you where you will use NO plus and where NO will come. Okay, so while discussing the examples, we can study those things. So these are the list of 3 classification of ligands. Now the next classification is, first classification was based on charge. Now the second classification is based on denticity. Based on denticity. So what is meant by denticity first of all? It is the number of donor atoms in a single ligand molecule to which it bonds with central atom. Denticity means the number of donor atoms to a ligand. Okay, the number of donor atoms in a single ligand is called as denticity. Suppose if a ligand has only one donating site, only if one donating site is there for a given ligand, then that particular ligand is called as unidentate ligand. So you see here, NH3 is a ligand and NH3 has one lone pair on nitrogen. Only that electron, those electrons can be donated to the metal. So only one donor site is there. So it is called as unidentate ligand. And if a ligand has 2 donor sites, then it is a didentate ligand. So here in this example, in ethylene diamine, so for one ethylene diamine, 2 donating sites are there. So since we have 2 nitrogen, so the electrons can come from both the sides. 2 electron pairs are there. So it is a didentate. And you see one more example. It is oxalate. C2O4 2- is oxalate ligand. So one oxalate contains 2 oxygen donor site. So oxalate is again a didentate or bidentate ligands. You can call it as didentate or bidentate. Both are correct only. So two donor atoms in both ethylene diamine and oxalate. So they are called as bidentate ligands. So the abbreviation for ethylene diamine is EN and for oxalate is OX. And for oxalate you have to use OX. Okay. So clear about the denticity. So I have discussed the unidentate and bidentate with you. Now I'll discuss one more thing under denticity, that is polydentate ligand. If a ligand has more than 2 donating sites, if a ligand has more than 2 or I can say more than 4 donating sites, okay, 3 donating sites means it is a tridentate ligand, and if it has more than 4 donating sites, then they are called as polydentate ligand. The very important example for polydentate ligand is EDTA4-, which is called as ethylene diamine tetraacetate ion. Okay, so what can be the structure of this molecule? We have ethylene diamine. So what you do, first write the ethylene diamine. It is CH2, CH2 and NH2, NH2, right? So this is ethylene diamine. Now what we have to do, from this ethylene diamine, you have to replace the 2 hydrogen atoms which are attached to the nitrogen by the acetate group. What is the formula for acetate group? It is CH3COO-, right? So one of the hydrogen from this CH3 will be substituted with this. So here CH2COO-. So tetraacetate, right? So all 4 hydrogens are substituted by 4 acetate, CH2COO- and CH2COO-. So this is the structure. Okay, ethylene diamine tetraacetate. So in this structure, now let us calculate the number of donating sites. So negatively charged sites are donating sites. So 1, 2, 3, 4, and also some neutral sites are there. Nitrogen has lone pairs, right? So 2 nitrogens are having 2 electron pairs, which are also the donating sites. So totally how many donating sites are there for this molecule? 6, right? It is a hexadentate ligand. So you can see the structure which I have drawn. It is a hexadentate ligand. Since there are 6 donating sites, it is a hexadentate ligand. So this was the question asked from this lesson in 2021 NEET exam. Okay. So this was the question. So what was the question? EDTA is a, the question was like this. EDTA4- is a dash. This was the question. So option 1, unidentate ligand, and option 2, bidentate ligand, option 3, hexadentate ligand, like that they gave option 4, etc. Okay. So the answer was hexadentate. Such an easy question, right? Where you can get 4 marks so easily within a few minutes. So this was one of the previous year NEET question, and easy questions are asked for both JEE as well as NEET from this particular chapter. Okay. So without any confusion, you can get the good marks from this lesson, which has more weightage also. Coordination compounds lesson, so having more weightage, so you have to concentrate more on this. One among your inorganic chemistry lessons. Okay. So in your class 12, only 2 inorganic lessons are there, right? One is D&F block and the other one is coordination compounds. And now also they have reduced the syllabus for both the NEET and JEE, no? So just concentrate more on both the lessons, which has more weightage. Got it? Now I'll go with the next type of ligand, which is ambidentate ligand. So what are ambidentate? When there are 2 donor atoms in a unidentate ligand, when there are 2 donor atoms in a unidentate ligand, at one time only one can donate. Okay, but there are 2 donating sites. Then either of the 2 ligand can donate electrons to the central atom. So those ligands are called as ambidentate. There are 2 donating sites, but at a time only one site can act as a donating site. Those are called as ambidentate. So let us understand this more clearly with the example. So you can see NO2. What is this NO2? It is called as nitrito or nitro. We have seen in that list, no? So this is nitro, which is a negatively charged ligand basically. Now, NO2 has two different types of donor atoms, but at one time, only one atom can act as a donating site. So here in the first case, nitrogen is donating the electrons to the metal atom. So it is called as nitrito N. In the other case, oxygen is donating the electron to the metal atom. So it is nitrito O. It is called as nitrito O. Clear? So able to find the difference between polydentate ligands or bidentate ligands with ambidentate ligands, right? So bidentate ligands can donate 2 electron pairs or 3 electron pairs at a time for a single ligand. But here, a single ligand can have only one donating site at a time, but there are two different donor sites, donating atoms. So this is one example. And the second example is SCN. Thiocyanato. SCN is called as thiocyanato, where in the first case, sulfur is donating the electrons, so thiocyanato S. And in the second case, it is thiocyanato N, because nitrogen is donating. Okay. And the third example is cyano, where the donation is done by carbon. And in the second case, the donation is done by nitrogen. So it is isocyano. Isocyano. Clear, students? So these are ambidentate ligands. And one more is also there, which are called as chelating ligands. So before moving on to the nomenclature, I want to let you know about the chelating ligands also. So what is meant by chelating ligands? Chelation. Chelation means ring formation. What is chelation? Chelation means ring formation. So the ligands which are able to form the ring with the metal atom, so those ligands are called as chelating ligands. So there is one very important point related to this chelating ligand. Chelating ligand containing complexes are more stable. Chelating ligand containing complexes are more stable. So why they are stable? Let me explain you. Yeah, let me take this. So you can see ethylene diamine is also an example for chelating ligand. So why I am telling this as chelating ligand? Because when it is bonded with the metal atom, it is forming a ring, right? So 1, 2, 3, 4, 5. So a 5-membered ring is formed by this ligand with the metal atom. Okay, ring forming ligands are called as chelating. So now this particular complex is stable when you compare the metal NH3 complex. Why? This is not a ring forming ligand, whereas this is a ring forming ligand. So this is more stable and the first one is less stable. So why it is like that? Less stable, more stable means in the solution state. Okay. Stability I am talking in the solution form. When you put this in the solution, ring forming ligands are more stable, because when you put a particular salt or a particular coordination complex into the water, which is a solvent, or in a solution, so bonds will be broken down, right? So metal ligand bond here, they can broken down. So here also, this bond can be broken down. So if this bond is getting broken down, so this particular NH3 molecule will go into the solution. It cannot come and form the bond with the metal atom. Okay, the one which is left is left, that's all. But whereas here, for chelating ligand, if the bond is broken down, so this connection will go off, but still one more connection is there, no? Because of this bonding, the ligand is still bonded to the metal. Okay, so the given complex is more stable because it is connected with the metal for a long time. So it is more stable. Chelating ligands are more stable compared to the normal unidentate ligands. Okay, clear? So from this you can get question because this concept is very important. The question can be like this. They will give you 4 complexes in 4 options. They will ask you to find out the complex which is more stable. Okay. So what you have to do? You have to check for the ring forming ligands like didentate, bidentate, tridentate, hexadentate. Except unidentate, all other dentate ligands are able to form the ring. All are chelating ligands only. Okay. So in 3 options, you can find the monodentate or unidentate ligands attached to the metal atom. And only one option you can see the tridentate or polydentate ligand. So that option is correct because that is the stable compound. Okay. So yes, I hope the concept is clear. So the last point alone is not there in the slide. Just take down the information about the chelating ligands. Got it? So if you have any doubt, you can ask me. Class 12 students are so silent. Not at all asking doubts. Fine. So go and read the thing which I have discussed. So since we don't have time, I'm not moving into the nomenclature today. So I'll continue this in the next class. On Monday, I'll continue the nomenclature. Okay. So the first 3 topics. What are the first 3 topics? The basic Werner's theory. So Werner's. So the summary for today is the Werner's theory, and the second is some basic terms. The third is about the ligands and the classification. So what are the 3 different types of ligands? First is on the basis of charge. Second is on the basis of denticity. And third is your ambidentate ligands. Okay, on the basis of the donor atoms. So they are ambidentate. So these things you study before coming to the next class. And in the next class, we can discuss about the nomenclature of coordination compounds. Okay. Clear? If you have any doubt, you can stay in the call or you can leave. Thank you so much, students, for listening the lecture. So meet you all in the next class. Thank you so much. Thank you. Yeah, thank you.